There we are. Did anybody do the calculation? Did I get it right?
Oh, I forgot to take into account.
Yeah, it's going to be the cosine of a negative value, right?
Yeah,
Yeah.
it'd be 111.
So
I did it for a positive.
okay. Yeah, so it has to be over 90. It looks like it's negative, and yeah, okay, great. So we're also going to be doing the classic. We're going to be doing the classic physics-style problems where force is a vector, or we treat vectors like forces. So this is the three dogs problem here, and we've got them fighting over a juicy steak. So in an equilibrium problem, what do all the vectors have to add up to?
0.
They all have to add up to 0. In other words, they all have to wind up.
Cancel each other out.
They have to cancel each other out, exactly. Yeah. So when I draw this, this is going to end up being a triangle. So dog A pulls with a force of 300 newtons to the west. And I know you can't see me drawing this right now, but hopefully you're drawing it too. Dog B pulls with 400 newtons to the south. So dog C has to complete that triangle. And then we have to figure out what the magnitude and direction of dog C's pull is. What's good about this one, it's set up, it's just a SOHCAHTOA problem at this point. Hey Luke, can you guess the, just looking at it, can you tell the magnitude of the dog C's pull?
Yeah. Square root 250,000.
Yeah.
500. 3 4 5 triangle.
Yeah.
Just to pick up the 0. Just shove a bunch of zeros in there.
Lots of extra zeros. Yep.
They
And
make long after
Good. But then you wouldn't be fighting the steak as much.
so you sound like a munchkin or something, Meg.
No, it's another one.
Oh my goodness, are you breathing pure helium?
No, I
Oh.
just did a weird voice.
Okay, all right. Yeah, sorry, you
Really?
were trying to freak me out there. Okay, what should we do to get the angle of that?
Toast of 400 over 500.
So yeah, we could just do the inverse cosine of 400 over 500. So not too hard.
I just noticed your review BQ.
Yeah, we should have a barbecue.
Okay.
Well, used to have those actually, where you have a barbecue and do a review. They're kind of fun.
I think we should do it.
Okay.
Back to school for it, I promise.
So we have the basis vectors hat I, hat J, and hat K. So just recognize you can express algebraic vectors as the sum of the basis vectors, okay? So the unit vectors that are along each axis. Dot product has lots of algebraic properties that behave a lot like the field of numbers. So they have distributive properties. You can use the dot product to find the magnitude of a vector. You can also use the dot product to find the angle between two vectors. So originally the dot product was defined in the course as A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between the two vectors. Okay. So I've got an example question here. Magnitude of A is 5. The magnitude of B is 4. The angle between A and B is 50. Uh-oh. And and I'm missing a bracket. So so we need to find the value of A plus B dot 2A plus B. Okay. So how are we going to tackle that? What do you want to do first? Luke, I'll put you on the spot.
Sorry, it's A times B times 2A times B?
Sorry. It's A plus B
Yeah.
dot 2A plus B. Sorry. Is that hard to see?
Yeah, it's just like a vertical line. I can't see the Australia.
Oh, I see. Yeah. Okay.
Yeah, I can't really see them on this.
Okay. Then let me quit doing that then.
It's too fine. They can have them.
RJ's the only one with vision.
No, not really. Sounds good. Computer.
Yeah, I think so. I think it's the cool headphones actually.
Okay, like that. That color too.
So A is 5. Sorry, the magnitude of A is 5. The magnitude of B is 4. Okay, the angle between A and B is 50 degrees. And what we need to find is the value of A plus B dot 2A plus B. So this is one of those questions where you have to have a little bit of faith that you've been given enough information to actually figure out what's going on. Okay, so let's do this dot product. Just remembering that dot product follows sort of the distributive property. So this is 2 times A dot A plus A dot B plus 2 A dot B plus B dot B. Now we can go into the simplification step. So when I take the dot product of a vector with itself, what does that actually tell me?
Zero, is it?
If I did the dot product of a vector with a perpendicular vector, it would be 0. But a vector with itself, yeah. Okay, there we go. Yep, so that tells me the magnitude squared
We absolutely took B squared.
Yep. Okay, so it's starting to shape up pretty well. I've got a value for the magnitude of A. I've got a value for the magnitude of B. I'm still a little mystified though. What's this? How am I going to figure out what A dot B is?
A dot B is the magnitude of A plus magnitude of A plus B times cos.
That's right.
Yeah.
Magnitude of A times the magnitude of B
Yes.
times cosine of 50 degrees. So that's 20 times cosine of 50. And what did I say B was?
4.
Did you get a number for me, RJ?
I got 104.58
4.58.
for the entire thing.
Sounds about right. So what you got, Meg? Thumbs up if you agree with RJ. Everybody? Well, thumb up from Luke. Okay. Yeah, that sounds about right. Cosine of 60 is 1/2. So this is going to be a little. It's going to be a little bit more than 1/2 of whatever 60 is. So it's going to be about a little under 40. So yeah,
38.58.
perfect. Okay. We're getting there. Yeah, I'm going to do bad quality screen sharing again, I guess. Okay, so Meg, you'd already alluded to this fact. When two vectors are orthogonal, orthogonal just means that they are perpendicular to each other. The dot product is 0. And the dot product is 0 because the dot product involves the cosine of 90 degrees. And the cosine of 90 degrees is 0. So we wind up exploiting that property an awful lot when we get doing the calculus and vectors. Okay, especially when we're dealing with planes and lines and finding distances from points to lines. Okay, so here's an example of using the dot product and the 0 value of orthogonal vectors. Find the value of A such that the vector 2, 4 and 2A are orthogonal. So you can probably guess at that. So 2, 4 dot 2A, these are orthogonal, and so what does that have to be equal to? 0. Yeah. Guess I could have made up a harder example, huh? Okay. How can you tell when Cartesian vectors or points are collinear? So we've got 3 points there. A is -2, 1, and 4. B is 3, -1, and 3. C is 8, -3, and 2. And the question is, are AB and AC collinear? So how can we go about figuring out if these are collinear? If I did my job, actually, they're collinear, but how do we find that out for sure? Meg, what do you think? What should we do?
Dot products.
Dot-
Something.
Dot products? RJ, any ideas?
I forget. It's been too long.
It's been too long. Okay, Luke, you're our last hope.
Give me a minute, I'll go through my notes.
Any ideas? What we should do? No? Okay.
We should draw it.
Actually, yeah. Oh, we've got man left.
Our last coach is Krista.
Maybe that explains why he was being so quiet.
Yeah. No, he's just ignoring me.
Okay. What we need to do is we need to figure out what AB is. We need to figure out what AC is. And then we have to find out if one of these is a scalar multiple of the other. Okay?
Oh, I found it. I found it. Just maybe look at my notes. What? It's like tail minus, or tip minus tail.
That's right. So we're going to take the tip, we're going to subtract the tail. So
And I have to
AB,
find where- right.
AB is equal to that. AC is equal to that.
Hey,
Oh, welcome back, Luke. I'm afraid maybe we'd made you mad or something. Five, -2, and 7. And oh no, I did get them.
it should not be 7, it should be a 1.
-1.
Yeah.
Uh-oh. This last one, did I do it wrong?
AB.
No, AB.
Oh,
The
this
red
one.
-1. 3 minus 4.
It's not 7.
Oh, okay.
-1, not 10.
Okay.
That's a 1, not a 10.
One.
It's a 1.
Yes.
3
Okay.
minus
3 minus
4.
4 is -1.
3 minus 4 is -1. Well, when did they change that?
About 7 centuries ago.
And is that last one -6? It is.
Yes, I wrote down my thing.
No.
It's not?
Oh, no, it's not.
Negative two.
-2.
Oh, geez. When did they change
The
that?
V in the tip should not be -2. It should
Oh,
be
that should be 2. 2 minus 4. Okay, all right. Hey, what do you know? Okay. We don't have to be upset. Okay. So AC is equal to 2 times AB. So these vectors are collinear. Okay, if they're just vectors, as long as they're not position vectors, they have the same direction. This one, AC, is just a scalar multiple of AB. That doesn't necessarily mean, well, yeah, that would mean the points are collinear in this case. Okay.
I was muted there, sorry.
Yeah. Does that work out okay, Luke?
Yeah, that's good.
What are they?
Oh, wait, never mind. That's the problem.
I didn't leave.
No, but if you look at the group chat, though.
Well, there we go. We've got a back channel going here. Okay.
I don't.
Okay, so you can see that that my country accent has drifted into the review here. Finding a unit vector that is the same direction as a regular vector. What do I mean by a regular vector? Okay, so let's just take a look at A and let's turn it into a unit vector. So I'll stop sharing my screen. Hey, you know what? I don't know if you guys have noticed or not, but I've gotten pretty good at not sharing my screen.
Didn't I have to point out yesterday?
Only once.
Did
Only
Oh,
once.
because Megan kind of went.
you hear me?
You didn't even mention it.
I wasn't going to because you couldn't hear me.
I could.
All right, that's enough small talk, you guys. I want the unit vector that is parallel to that vector. What do I need to do?
-2 ij 4k.
Nope, that gives me the vector expressed in terms of the 3 component unit vectors. I want to turn this into a vector that is 1 unit in length. So
You
I
gotta
want,
put it into Cartesian 4 million, or
what's that? So it is in Cartesian form.
well, do you find the slope or whatever?
Well, we have to find the magnitude of A. So we're going to do the, you can either do the dot product and take the square root, or you can use the Pythagorean theorem. What's that? Square root of something ugly, 21. Okay. So the unit vector is actually
4.58.
So you actually can write it like this. So there's the unit vector in the, it's in the same direction. So we've turned it into something that's 1 unit long. Occasionally it's useful. All right. Hope everybody got that. So I've gotten, we won't have we won't be too deep into the cross product. But the cross product produces a vector that is perpendicular to two vectors. Right now that seems pretty much just like a curiosity, but once we get into planes and lines, that becomes something that's fairly useful. We can find the magnitude of the cross product. The magnitude of the cross product is actually just the length of the line. And then I haven't put a question on yet, but you can use the dot product to find the projection of one vector onto the other. Okay, so that should pretty much cover it. And I drew the questions sort of just out of the exercises at the end of each of the units. So it can't hurt to do that when you go to study tonight. Are there any questions about the test tomorrow?
Do you have to draw all the? You said something about drawing every diagram, or?
Just when you start the problem, just draw some vectors. That's about it. So like, you know, if it says A is 5 and B is 10, draw a couple of vectors A and B.
Right.
Mostly because it helps you.
Right.
Yeah. So there's it's nothing too earth-shattering. Any other questions? Meg, all good?
I still am doing something before.
It's all thumbs up?
Yeah.
Okay. And once again, we'll try and start right at 2 o'clock. I don't think it's going to be particularly long, but we'll try and start as close to 2 as we can. Okay?
I will be there tomorrow.
Okay. All right. We'll see you guys tomorrow then.
I still don't get a sign up for them. I think I'm missing something.
Yeah, sorry?
I think I'm missing something for sign up for.
Oh.
I did draw it out this time.
Sorry?
I did draw it out this time. I'm still missing something.
Okay. All right. Okay, if you want to hang on, we can, if you want to show me what you drew, that's okay.
Alright.
Okay. So we'll see you tomorrow. See you tomorrow, Luke.
Yeah, I'll see you guys tomorrow.
Bye. See you, Meg.
Bye.
See ya.
Yeah.